Great. Well, so as Dave said, this is an extension from our work last year where we tied single wells to seismic traces with dynamic time warping. And this year, we're now trying to do this with multiple wells and still automatically, but this time simultaneously. Traditionally, geophysicists will tie wells individually and then just try to manually correlate them. And we're trying to automate this process. So the first thing is, logs are sampled at a much finer vertical resolution, have a much finer vertical resolution than seismic. And this creates some obvious differences between them. And we want to combine these two types of data, right? Because we have different measures in seismic and logs. And one of the hardest parts about tying logs to seismic, though, is the fact that logs are sampled in depth and seismic is sampled in time. And there's still a lot of people that work in time-migrated seismic volumes. And so in order to tie well logs, we need to create a mapping from time to depth. So we want something that looks a little bit like this. So what I'm showing you here is not a 1D profile. This is a 2D depth as a function of time. So this image here is generated from 5 1D time depth profiles from 5 different wells, interpolated. And so we have depth as a function of time, and we can use this mapping to tie logs to time-migrated seismic data. So how do we make this? Well, the first step is we need to tie well log to the seismic. So in order to do that, we need to first create a reflectivity from the logs, from the velocity and density logs. And then, to simulate the seismic, we generate a synthetic seismogram. And we're using the propagator matrix method. We're just computing normal incidence plane waves. And this is nice because it gives us internal multiples, and we can make a constant Q assumption, frequency independent Q, which makes it the synthetic seismogram slightly more realistic than just if we were just to convolve some wavelet with a constant peak frequency. So we want to tie these synthetic seismograms, relate them to seismic data. So this is a seismic. This is an inline slice from the Teapot Dome dataset, 3D dataset, and it's chosen to coincide with the well log that I just showed you, right where that oil derrick is. So if we create a synthetic seismogram and try to compare it to the seismic image here, and I've just replaced a trace here in the seismic image so you can compare the synthetic seismogram. And if I take off this little box here, we can see that the reflectors don't really match up with the seismic traces. And this is due to a couple of errors. First, we have the biggest error is the error in the estimation of the velocity overburden. So the wells only logged from in a certain depth range, and we don't have the velocity information all the way to the surface. So we have to estimate a static shift to tie the synthetic seismogram. There's also some stretching and squeezing that we need to do to compensate for errors and the log interval velocity and like seismic velocity. So if we were to use the algorithm that I showed last year, the methodology I showed last year, where we tie the synthetic seismogram to seismic traces with dynamic time warping, then we get something like this. So we can now see that the reflectors are much better aligned, and there's quite a big static shift in the tie. So if we go back and look at the initial synthetic seismogram again, I pointed to a few reflectors you can keep your eye on. And if we look at the single tie, you can see again that it's quite a large static shift. And there's also a little bit of stretching and squeezing in there. So once we tie the well to the seismic, we can get a time-depth relationship. So we have an initial time-depth relationship, which we estimate by just integrating the slowness from the log. and we estimate the initial static shift just using some shallow velocities and for using statics and some shallow log velocities. And then once we tie the well, we get a new updated time depth curve, which is shown here in red. So there seems like the biggest change here again is this static shift, and this is just showing that we had a really large error in our velocity overburden, and that's what we're correcting, a big error we're correcting for in well ties. Another thing, which is a little harder to notice, is change in slopes between these time depth curves. And those changes in slopes are related to the stretching and squeezing that we're applying with dynamic warping. And if we were to take the derivative of this to look at the slopes, we would get the velocity. So the black, which you can't really see too well, is the black velocity curve on the right is the log velocity. And the red is the updated velocity after we tie it. And so increases in velocity, in this updated velocity, correspond to squeezing, and decreases corresponds to stretching for our well tie. And so the reason that it's not changing very much from one to the other is because with smooth dynamic warping, we can better constrain the algorithm to not allow for large changes in these updated velocities. And the way we relate that is a similar way that Stefan did, with the derivatives of the time shifts equal to the ratio of these ratio minus 1 of these two velocities. And so we can constrain the time shifts in the warping, and we get a much better constrained well tie. So we could do these well ties for every well in the Teapot Dome data set. And conventionally, this is what a lot of geophysicists do. They do individual well ties and then manually correlate them. So how would we possibly handle multiple wells simultaneously? And the main thing that we need is a way to laterally constrain our well ties, because as of now, we're only vertically constraining the time shifts that we're using to tie the wells to the seismic. So in order to demonstrate our method, I'm going to be using 5 wells, which are shown here as yellow dots. And these are posted on just a constant time slice from the 3D Teapot Dome data set. And the yellow curve that's going through them is a seismic image that I'm going to extract from the 3D data set that coincide with these 5 wells. And we can do all the following steps I'm about to show you in 3D, but it's so much easier to show you 5 different wells in one slice with a 2D example. So the reason I chose these wells is this first one is the one that I showed you for the single well ties. These next 2 are very close to each other, which if we're trying to laterally constrain the well ties, then these could pose some issues. And then the 2 on the outside are both limited in depth ranges, and they're logged at very deep intervals, so they're going to have a large error in the overburden velocity. And then the seismic slice itself and the blue arrow is going through a fault, which is shown in the blue arrow, and you'll see this better in the vertical section. And in the red arrow showing the classic Teapot Dome anticline, is pointing to the where it will show up in the seismic time slice. So if we look at the vertical slice extracted along this yellow curve, we can see that fault that I showed in blue and the anticline in red. And I wanted to have these structural features to show some of the lateral limitations or problems you might encounter when trying to do multiple well ties. And of course the wells are posted here at the oil derricks in yellow again. So if we generate synthetic seismograms using the propagator matrix method, as I showed before, for each one of these wells, we have these initial synthetic seismograms, which are all different lengths, and of course some of them have a larger estimated static shift, and it's because they're logged at a deeper depth. And so we have a lot of variety here. So now if we want to tie multiple wells simultaneously, then maybe we want to tie them individually first to try to get them close, at least try to get a good estimate. Maybe we put really tight constraints on our stretching and squeezing, and try to mostly get a bulk shift, a static shift, and try to get them in the ballpark. So if we tie each one of these individually, then we can see that the reflectors and the synthetic seismograms now line up pretty well. You can see a lot of consistency between each synthetic seismograms, and notice the large static shift from the initial to the single ties, especially in the wells on the outside of the image. So if we remove these, we can remove this. We want to try to find a way to laterally constrain these single ties. So the way we do that is to create a new type of synthetic. And this new type of synthetic is just interpolated synthetic seismograms. So the way we interpolate these synthetic seismograms is very similar to how they presented the image-guided interpolation. So we first compute a structure tensor field from the 2D seismic image that we extracted. And then, using the structure tensor field, we take the synthetic seismograms and we interpolate them along the structure tensor field to get a synthetic image. And this is a synthetic image from interpolating the synthetic seismograms with the structure tensor field. So notice that because the wells on the outside are in limited depth ranges, we don't have any data above these synthetic seismograms or below them. And so we've just got holes there in the synthetic image. And you can see that there's a pretty decent correlation between some of these synthetic seismograms. You can see some continuity of the reflectors, and that's because we've tied the wells individually, and some of them should line up fairly well, as we would expect. And so this synthetic image is what we're now going to tie to the seismic image. So like we tie the synthetic seismograms to the seismic traces, we're going to use dynamic image warping to tie the synthetic image to the seismic image. And if you just flip between the synthetic image and the seismic image, you can see some similarities between the seismic and the synthetic image. We would imagine that we won't, because we've already tied the wells individually, we won't have to do too much bulk shift, maybe just some more stretching and squeezing. And so if we were to if we tie the synthetic image to the seismic image using dynamic image warping, we get a warped synthetic image. Now this image looks a little funky. It's got a lot of bends and folds and some interesting characteristics, and these are just diagnostic of where the synthetic image didn't match the seismic image. And so dynamic image warping is shifting the synthetic image to try to match the seismic image, and that's what these little bends are indicating. So now if we look at just the wells, which is the only place we have our time-depth relationships at each of the well locations, and we extract seismograms from this warped synthetic image at each of the wells, then we get these warped synthetic seismograms, which gives us our final time-to-depth relationship. So we can estimate our time-depth from the time shifts used to create these warped synthetic seismograms. And and so the way we get here again is we compute the initial synthetic seismograms, we tie them individually, and then we interpolate them along using image-guided interpolation to get a synthetic image, which we then tie to a seismic image using dynamic image warping. And then now we can extract synthetic seismograms at each of the well locations. So if we reinterpolate these synthetic seismograms, which are tied using dynamic image warping and individually tied previously, then we can, and we interpolate them along the same structure tensor field I showed you, we can get a sort of an updated synthetic image. We would expect the synthetic image to look similar to the seismic image if we've tied it well enough. So if we compare to the seismic image to this reinterpolated synthetic image, we can see that a lot of the reflectors are lining up fairly well. So now if we want to compute these updated velocities like I showed you before, we tie the the log velocities to the seismic using the time depth relationship at each one of these wells, and we get these log velocities. So now if we want to see the lateral consistency between these log velocities, and maybe that'll give us some hint on how well we tied the wells, we can use the same structure tensor field and interpolate these these tied log velocities and interpolate them along structure to get some interpolated velocities. So notice that on the left side of the image, we've got pretty good consistency. The features and velocity are fairly laterally consistent. But then when we get over to the right side of the image, if you look at about 0.8 seconds where I've highlighted, we've got a big discontinuity here. And we're going from about 3 kilometers per second to around 4.25 kilometers per second. And that's a really big jump. And so the way I've seen this, the way I've interpreted this is that it's diagnostic that we're not tying that outside well that's limited in depth ranges very well to the seismic image. So where did we go wrong? So these were our steps here. We computed the initial synthetic seismograms, and then we tied them individually, and then created a synthetic image from those ties and tied it to the seismic image using image warping. So the place where we went wrong was in fact the single ties. So if we don't do that step where we individually tie the synthetic seismograms to try to get them close to the right answer, we're actually going beyond what the image warping beyond the lateral constraints of the image warping, and it can't correct our mistakes from the single ties. And I mean, this makes a lot of sense. There's a lot of error in estimating that overburden velocity with just using one or a few seismic traces to try to tie a single well. So now if we try to redo this workflow, excluding the second step, we have our seismic image. We compute the initial synthetic seismograms just like we did before, but now instead of tying them individually, we take these initial synthetic seismograms and using the same structure tensor field, we interpolate them to create an initial synthetic image. And so now you might notice that these reflectors aren't really as continuous as they looked before. That's because we haven't tied these synthetic seismograms to the seismic traces at all. And so these are all tied using this initial time depth curve. So instead now, if we try to tie this initial synthetic image to the seismic image, then we get a warped synthetic image, which is now bulk shift, which now has a large static shift to compensate for the overburden velocity. But this image is laterally constrained and vertically constrained. So these little bends and folds again are indicative of where the image needs to be tied better. So where we're tying the synthetic image to the seismic image. So again, if we take the seismograms at each one of the wells, we have the time depth relationship for each of the well locations, and so we get these warps. We get these synthetic seismograms again at the very end. And so again, the way we got here was just generating the initial synthetic seismograms, interpolating them along the structure tensor field, which we got from the seismic image, and tying that synthetic image that we create to the seismic image. So if we reinterpolate these synthetic seismograms along the same structure tensor field, we get a synthetic image again, and this is you can see a lot more correlation than our initial synthetic image. And if we compare this to the seismic image, then we can see again good correlation. I mean, and this one it's a lot better, but it's still hard to tell, and that's why we need the velocity to check the velocities again. But if we go back and check and compare this new synthetic image to the one we got with the single ties, which is shown here, and if I flip back and forth from this one where we have the single tie step to the one where we skip the single tie step, you can notice that the well on the very right has a large static shift that we're adding, and that's because of the single well ties. So this is a great improvement from when we got our initial guess wrong with the single well ties. So if we again were to get the synthetic seismograms, we have the time depth relationship at each one of the wells. We plot the log velocities with our updated time depth curves, and now and this is just from the initial synthetics tied, the initial synthetic image tied to the seismic image. We tie the log velocities to the seismic image, and then we interpolate them along the structured tensor field. We can now see that with our new time depth curve, with a simpler method, we get better correlation, especially in this low velocity layer. And there's some little higher velocity things, and if you look at these images for a while, you'll see that this one has much better correlation laterally. Now, you may be looking at the top part of the image between maybe it's probably 0.5 seconds up to the surface. And you might see between wells 3 and 4 a pretty it looks like a fairly significant discontinuity in this velocity. And this is because we're trying to tie these logs to a really noisy part of the seismic image. And so whatever stretching and squeezing we're applying there is affecting the velocity, these updated velocities. And it's causing a poor match, a fairly large discontinuity here. And one way we can try to improve that is using something similar to what Stefan has done, where he picked large amplitude reflectors for his coarse grid points. And remember, we're using smooth dynamic warping for all of our tying. So to compare this to the interpolated velocities for single ties, we can see that there's a pretty large difference, especially in that well on the far right. And I'd like to say that these are improved from the single well ties to just skipping the tying the wells individually. So now from this, we have the time depth relationship at each of the wells. And so we can interpolate the time depth curves to get our mapping from time to depth. And again, this is depth as a function of time that we're showing, and it's not a 1D profile. It's just really well correlated. And there's a little bit of structure in this picture if you plot some contours on it. So I wanted to thank the C team for all of their wonderful input. Thank you, all you sponsors, for doing everything for us, sponsoring us, showing, giving us all sorts of ideas, giving us data, giving us everything. So I appreciate everything. And then, of course, the Rocky Mountain Oilfield Testing Center for publicly providing the Teapot Dome data set and all the well logs that we've used. And again, we've done this in 3D many times and are working on refining it more in 3D because we can laterally constrain the dynamic image warping in 2 directions in 3D. But I felt this 2D example would be the best to show during the presentation. So thank you for your time, and I'd be happy to answer any questions.